Welcome to this episode on the use of complex numbers in electrical engineering. In this series, we've been learning how to look at and understand circuit schematics, in particular analog circuits such as this guitar amplifier. And we learned how to parse the schematic and figure out what each little section of it was doing. For example, C1 is blocking DC but letting the AC signals through. And C2 is shorting out high frequencies. But what does that mean? How does that work? Well, that's what we're going to talk about today, and we're going to employ complex numbers to do it. So this cover slide may look a little busy, and it may look like a foreign language, because quite frankly, mathematics is a language. But by focusing on the how and why, as well as the math, I'm hoping that we can make that language quite understandable. Here's another example from the previous episode in this series. I bought a brand new oscilloscope and I tried to use a microphone with it, and all I got was this horrible noise. But by designing and building a simple little circuit that you see here placed between the scope probe and the oscilloscope, which is on the right side of this dotted line, here it is physically, we're able to take that horrible noisy waveform and turn it into this, which is what we're looking for. This is the tone coming out of the synthesizer. And if you've seen those other episodes, you know that this is a low-pass filter. And today we're going to talk in detail about how that works. And that's what all this mathematics is for. Okay, let's get into today's topics. I'm going to present complex numbers in a way maybe you haven't seen or thought about before, and I'm hoping that that will make it more understandable, the language. Then we'll jump back into circuits and talk about phasors, what are they and how are they used, and impedance that we've alluded to already, and how we use this in circuit analysis. And we'll use examples throughout this to illustrate. And we'll conclude with looking at that frequency response plot on the cover slide. So before I retired, I was teaching those radio design courses as well as electronics courses, but I was also involved in creating and teaching an Intro to Electrical Engineering course for incoming freshmen. And in that course, we covered the basics of electrical engineering, including all the topics you see here, but we also covered complex numbers and their use in impedances and their use in solving circuits like the ones I showed you. And here's how we covered that complex number material to get everybody up to speed. Apologies for the handwriting here. These are the notes I used when lecturing in the class, and the students had to, of course, write stuff down. And I don't like using PowerPoints in classes because it's too fast. So anyway, stick with me, and this is the last you'll see of my handwriting. To talk about complex numbers, we began with real numbers, things that we kind of already know or think we know. For example, you may have a real number A, which could be 5 or whatever, doesn't matter. Or a real number minus b, which could be -2, for example. And we can use those to represent like distances. So here's a number line, and a is a units to the right of 0, the origin, and minus b is b units to the left. So there's a concept of direction coming in here that we're going to see a lot today. But it really gets interesting when we talk about operations. So a minus b is, of course, a plus -b, and that means move a units to the right and then move b units back to the left. And that comes in handy when you're solving problems. And it's kind of intuitive. You drive a car this way and then drive it back this way and end up here. Okay, easy. But what does a times minus b mean? Well, we know how to manipulate stuff because we learn how to crunch problems, but what does it actually mean? What's it doing for us? Well, a times minus b means multiply the quantities a and b, so the 5 and the 2, for example. But the negative changes the direction. So the result is negative of a times b. Great, so we already know all this, so why am I talking about it? Well, because in complex numbers, we need that concept of direction change. But it's not direction change from the right to the left, it's in a two-dimensional space. So one view that you can take of a complex number is it's a two-dimensional number, or vector, if you will. So instead of just going right and left, we can go also up and down. And what that means is you can talk about a number which is written as, for example, a plus jb, and that means go out a units to the right and then go up b units from that, and you end up with this vector. So the number here, z, a plus jb, is this vector in two-dimensional space. It has a magnitude and an angle, and we'll talk about how to compute those today. Or, for those of you who already know a lot of this stuff, we'll review it. And then we're going to apply it to some electrical engineering problems, and not just simple problems. We'll apply it to ones that really matter. And you'll notice I haven't said anything about the square root of minus 1 up to this point. That's because I really don't like the square root of minus 1 personally. Square root of minus 1 can be represented as 1 at an angle of 90 degrees. And that's where this comes from. But I'm getting ahead of myself. So let's look at what we have over here on the right. This we're going to go through in detail today in the coming slides. So I'm not going to go over it right here. This is representations of complex numbers, and this is how you operate using those to multiply and divide and so forth. And this was a class handout that we gave. Down here are a few theorems and proofs. And this is not a math video. Well, it kind of is, but I'm not focusing on the math except as a way to actually do electrical engineering. So I'm not going to cover theories and proofs here. However, here's the slide. You can look at it. You can freeze this and read it if you have background to make sense of it. Let's move on. So here's what we need to know about complex numbers if we're using them in electrical engineering. First of all, in the ECE, electrical and computer engineering field, we use J instead of I for this square root of minus 1 thing. It's just a notation change because I is used for current in electrical engineering, and so we switch to J. All right, with that said, let's talk about representations. We already discussed that it's a two-dimensional number. So Z is out here in 2D space. There's two ways to represent it. We can talk about where it is in a rectangular coordinate system, so A and B, and we write that as A plus JB, and the J means that that's the term which is on the north-south direction. Or we can talk about it in polar form as the length of the vector and its angle from the positive x-axis. So we can talk about complex number Z as R at an angle of theta. If you've had some of this material in school, especially college, for example, you may have also seen a third representation known as the exponential representation, Z equals R e to the j theta. I'm not going to go into that today. But this does become important if you go into some more advanced courses on things like Fourier transforms. The conversions to go back and forth between them, which we're going to do, coming up on the next slide actually with some examples, are shown here. And this is just trigonometry stuff. The magnitude, R, in the polar form is found as the square root of the sum of the squares of the rectangular coordinate system parts, but not, you don't put the j in, right? So it's just a squared plus b squared square root. The angle is taken as the arctangent of b over a. So that will give you this angle right here. If your complex number Z is in this quadrant or this quadrant down here. If it's over here, you have to be careful about how you write this and punch it into a calculator. If you're computer programming, you would use something like an atan2 function to keep track of that. That's just a detail. Don't worry about that right now. And of course, going from polar to rectangular is just r cosine theta to give you A and r sine theta to give you B. Okay, if you're here for circuits, let's be done with this and move on to something that matters maybe to you. Well, hopefully it all matters. But this is what I'm calling real-world problem set 1. These problems that I've written here, 3 of them, are for a very simple circuit, a resistor in series with a capacitor. And I want to know what the impedance is. And there's going to be a little bit of surprise along the way here, perhaps. First of all, the capacitor's impedance. We're going to talk about impedance in detail in a minute, but it's represented in this case as minus J10K. And I'll derive in some coming slides how we get from the capacitance value to the impedance. And it depends on the frequency. So this is at 100 hertz. We have this 160 nanofarad becomes minus J10K ohms. And that's in series with 1K. And I want to know what the impedance is, but I want to know it in polar form with the angle in degrees, and you'll see why. And then we'll do it again at 1 kilohertz, and then again at 10 kilohertz, and compare them so we can start to get some understanding on how circuits, such as this, behave in detail, depending on the frequency of the input signals that are coming in. So to solve this first problem, I'll go ahead and tell you, impedances in series add, so this is an impedance, this is an impedance, we add them. So Z is 1K plus a minus J10K. So write that here, and if you're following along and you want to write this down before I show you the answers, then do so now, freeze it here. All right, here come the answers. So for the first one, at 100 hertz, a 1K resistor in series with a 160 nanofarad capacitor has an impedance of 1 times 10 to the third, this is calculator notation, 1 times 10 to the third plus negative j 10 times 10 to the third. And if I want to find the magnitude, I take the square root of the sum of the squares, so I have 1e3 squared plus 1e4, this is 1e4 squared, the square root of that. And then to get the angle, I take the arctangent of negative 1e4 over 1e3. Crunch, crunch, crunch. The calculator tells me it is 1.01 times 10 to the 8th. But I have to square root that, and I get 10.05K. And if I'm in radian mode on the calculator, I get this number out, but I want it in degrees, so I convert to degrees, and I get this using my calculator. So great. If you got this, then you get a check, but we're not done. We're not getting a grade in this video. What we're trying to do in this video is understand stuff. So here's the take-home from this. If you look at this, you have a 1K in series with a 10K thingy. And the result apparently is 10K to like 3 significant digits. So if I bring it out to 4 significant digits, it's 10.05K. But this is essentially 10K. That's decidedly different than your intuition might say, well, it's 11K at some angle, or it's not. It's basically 10K, and the angle is close to the 90 degrees of the capacitor. So if you think about this, the take-home is that when you have a series combination of a resistor and a capacitor, and the capacitor is substantially larger in impedance than the resistor, the capacitor wins. The net result looks like basically a capacitor of 10K at an angle of minus 84 degrees, which is close to minus 90 degrees, which is what the capacitor is by itself. So this devolves into just the capacitor to a reasonable approximation. One way to look at that and understand a little bit more is to plot the number. And here I've gone out 1K to the right and down 10K. And that's the number 1e3 plus negative j 10e3. So I'm right here. And that vector doesn't look too much different than if I had just gone down here. Yes, there's a little bit of an angle to it, but the length is almost identical. And that's what the math is telling us. Okay, I can do the other two problems much quicker now. This one is 1K in series with minus J1K because we've gone up from 100 hertz to 1 kilohertz, and the impedance of the capacitor dropped by a factor of 10 when the frequency went up by a factor of 10. So this is what we have. If you crunch it using the same procedure, you get 1.414K, that's actually the square root of 2K, at an angle of negative 45 degrees. So that's this little vector right here. So it's not 2K, but at least it's, you know, somewhere between these two, and it makes a little bit of sense here. All right. How about at 10K? Well, at 10K, the capacitor's impedance has dropped dramatically to negative J100 ohms. And that's now much smaller than the resistance. And when you crunch the numbers out, it comes out that, well, the big guy wins. In this case, the big guy is the resistor, and it's 1K. And the angle is negative 5.7 degrees, and that's not too much different than 0 degrees, which is what it would be for the resistor alone. So this circuit looks a whole lot just like the resistor. That's interesting. These are hopefully some interesting and useful things that you can take home from this problem set. Now let's move on to complex number operations. Addition, subtraction, multiplication, and division. So we have two complex numbers, Z1 and Z2. Z1 could be rectangular form or polar form, Z2 likewise. To add complex numbers, it's best to be in the rectangular format. So A1 plus JB1 and A2 plus JB2. And the result is you just add the real parts and you add the so-called imaginary parts. And subtraction is similar, but multiplication is different. In multiplication, it's best to be operating in the polar representation. You can do it in the rectangular representation, but you end up with like 4 terms that you have to then reduce down to 2, and it's just not very intuitive compared to doing it in polar form. In polar form, if you've got R1 at an angle theta 1 and R2 at an angle of theta 2, we just multiply the magnitudes and add the angles. So that's the rule. Division is similar. Z1 over Z2, if in polar form, means take the magnitude R1 and divide by the magnitude R2. And take the angle theta 1 and subtract the angle theta 2. And we're going to use that in an example here. Okay, so here is real-world problem set number 2. All right, we've got two impedances. One is a resistor and one is a capacitive impedance, minus J10K for the capacitor and 1K, just like before. So same components, just in a parallel form. Now, just like with resistors in parallel, to find the net result, here we take the impedances and take the product of those two impedances divided by the sum of those two impedances. So if you're following along, write this down and then use these rules. All right, now I'm going to go to the answer. Now, for the multiplication of the two numbers in the numerator, I did not convert to polar form because these are not fully complex numbers. This is a simple real number, and this is a simple so-called imaginary number. So I left them in this form, and I multiply these two numbers together. In fact, there are 3 numbers here. I can take the negative j and move it out front, leaving 1e3 times 1e4, which is 1e7. And then I take the negative j and recognize that that's 1 at an angle of minus 90 degrees. And so my net result is 1e7 at an angle of minus 90 degrees. If you're following along and working this out for yourself, you might want to draw these out on a piece of paper and think about the angles and so forth. But this is the result for the numerator. For the denominator, we have this. Oh, wait, we already solved that. So on a previous slide, we found out that that's 10.05 times 10 to the third at an angle of minus 84 degrees. Now I've got both of these in polar form, so it's simply a matter of taking 1e7, dividing by this, and I get 995 ohms. And I take negative 90 and subtract negative 84, and I get negative 5.7 degrees. And now we take a deep breath and forget about all this messy stuff and say, what's the upshot? We got a 1K ohm resistor in parallel with a minus J10K ohm capacitive impedance from the 160 nanofarad capacitor. What's the result? Well, the result is that it looks a whole lot like a resistor of 1K. And so when these two things are in parallel, the small guy wins in parallel situations. At 1 kilohertz, well, both of these matter, and we end up with 707 ohms at an angle of minus 45 degrees. Now up at 10 kilohertz, where the capacitive impedance has fallen to minus J100 ohms, this is now the small guy, so that one should win in a parallel combination. And in fact, it does. The result is 99.5, which is like 100, at an angle of negative 84, which is like negative 90 degrees. So 100, negative 90 degrees, that's just what the capacitor is. Okay, time to take a deep breath. Now we're going to go somewhat deeper, with the goal being able to do circuit analysis with sine wave signals on any linear circuit. And we're going to do that by talking about phasors and impedance, which we've been referring to, but we haven't fully defined yet. We will now. And this will cover the material that is fundamental to AC circuit analysis. It's fundamental to being able to understand in detail and quantitatively what's going on in these circuits that we covered in previous episodes. And over here on the right, we've got this low-pass filter, and we've said previously that this capacitor shorts out high frequencies. Well, what does it mean to short them out? How much do they get decreased? They don't just suddenly go to zero. So that's our topic next, is to talk about how you do circuit analysis so that we can eventually then do our frequency response plots and answer those questions. Okay, take a deep breath again, because we're going to be going into some fairly deep material here. We're going to write some expressions like we did in previous episodes for Kirchhoff's current law, nodal analysis. And we're also going to take derivatives. And we're going to define things like reactance and ultimately impedance, so that we can eventually then do circuit analysis and figure out what the so-called gain transfer function frequency response of this circuit is. So, here we go. If you need to pause it along the way, please do so. Hopefully you come back to it. But I wanted to try to get all of this material into one episode, because it all ties together and it's going to get all cut up if we don't. So pause it here if you need to take a break. Pause it anywhere if you need to take a break. And this is mathematics. It's another language. And so you may need to view things several times and kind of work some of those problems in order to get this material really embedded in our brains. Okay, nodal analysis. We have a circuit. There's a sine wave voltage, V sub source, Vs. And it's, in this case, a resistive voltage divider, but it's capacitively loaded. We did this circuit in a previous episode with a second resistor here, but now we're going to have a capacitor here, which is going to load it, but the loading is going to change depending on the frequency of the source. And here we sum the currents leaving node 1. And the sum of the currents leaving node 1, as we said in previous episode, need to be 0. That's Kirchhoff's law. So the first term of my expression here is this current going up through R2. The second term is this current going down through R1. And the third term is the current going through the capacitor. I'm assuming that there's no loading out here. And so the current going through the capacitor is C1 times the derivative of the voltage on this node with respect to time. If you haven't had calculus or you're not comfortable with it, don't worry about it. We're not going to use calculus going forward here. You could solve this using differential equations, which is based on calculus, and some matrix theory techniques, and it's really a mess. It's painful for large circuits. We're going to learn a way to do it without it. All right, we're going to use phasors and impedances instead. But we do have to get comfortable with some math expressions. This is a sine wave. This is the voltage across the capacitor, which in this circuit is just tied directly across this voltage source. It's a function of time. That's all this means. And the value is, at any given time t equals 0, for example, you put 0 in here, the value is v, the magnitude of this sine wave, sine 2 pi ft plus theta v. Let's assume theta is 0 and t is 0, so sine of this result, sine of 0 is 0, and so we start right here. All right, I'm not going to go through this in detail. Some of you know it, some of you don't, but that's how you work through it. And then you put a different time t in and you plot this thing out. So there you go. All right, so this is a sine wave. That's the voltage across the capacitor. What's the current going through the capacitor? Well, we're going to see what it is in a second. I've drawn the answer. It's going to turn out to be a cosine wave, and it's going to have some magnitude and some angle, which in general, the angle could be different than this angle over here, and it will be. I'm going to take a derivative to go from this expression to this expression, but we're only going to do that once. Henceforth, we're going to use what are called phasors. So, in phasor analysis, what we do is we use complex numbers to represent the magnitude and the angles of the sine waves involved in the circuit we're dealing with. So for VC, this is the magnitude. The vertical bars mean take the magnitude of, and this is the angle. And so we can write it in polar form like this. Or if we, for some reason, want to write it in rectangular form, we can use the conversions that we just practiced earlier to change it to V real plus J V imaginary, or V imag, because I hate the term imaginary. There's nothing imaginary about it. It's just a second coordinate in a two-dimensional number. And likewise for the current. Now, a very important point. This innocent-looking V here is not a function of time, and it's not a simple real number. This is a complex number, as elaborated here. And the complex number represents the sine wave with the frequency missing and the time dependence missing. It just tells us we have a sine wave which is of this magnitude and at this angle. So when we see this V coming up in the future, remember this is a complex number and it has this meaning. Now, why are we not carrying the frequency along with us? Well, we'll see in the future, but it hinges on one very important point, which is that for so-called linear circuits, which are the ones we're going to be dealing with, the frequency of everything in the circuit is the same if the excitations are simple sine waves at one frequency. So we don't have to encode the frequency in this expression. And likewise, the time. We don't have to include the time in the expression. What's important is just the magnitude and the angle of the sine waves involved. Okay, I told you this would be a little bit painful and that you should feel free to pause it because it takes a little bit to absorb math. How did I go from the sine wave voltage across the capacitor to the cosine wave current? And oh, by the way, why didn't I write cosine here? Well, I didn't write cosine here because in general, it's going to be a sine wave at an angle. So a sine at 90 degrees is a cosine. And so I can express it like this. I don't have to write cosine. But let's see the cosine. From physics, the current through the capacitor is C dV dt. For those who have had calculus and want to follow along where all this mess came from, what I did is I took the expression for the voltage here, Vc of t, and I put it into the derivative. And then I took the derivative of this, and the derivative of sine is cosine. That's where cosine is going to come from. And according to the chain rule, I use cosine of what's in the parentheses, and then I pull out front the derivative of what's in parentheses, which is 2 pi f. So here it is, cosine of the stuff times 2 pi f times c, which was here, times v, which was here. All right, so that's where that comes from. And we said cosine could be written as sine with an addition of 90 degrees, so that's how I got from this middle expression to the right-hand expression. Okay, now here's what matters. I can pull out of this the stuff that matters for the phasor. This is the magnitude of the current. This is the angle of the current. Let's just consider first how the magnitude of the current relates to the magnitude of the voltage. Well, magnitude of current, I, here, is equal to this piece that's underlined. So I've written it here. So that's how I got that. We'll worry about the angle later. With this expression, I can rewrite it using a tiny bit of algebra as V equals I times 1 over 2 pi fc. And that looks a lot like Ohm's law, V equals I times R, with this taking the place of R. This is what we call the reactance, X sub C, that I've talked about a lot in previous videos. It's very important because it does include the frequency dependence. So the X sub C value that you use in calculations is going to change with frequency. We don't have to drag it along when we're solving the circuit using phasors at a particular frequency, but we do have to understand that the results are going to be different at every different frequency. That's what makes this stuff fun. That's what makes it useful. What allows us to have things like low-pass filters. Cool. So this expression for the reactance of a capacitor is critical to understand and to know. Commit to memory. But it only relates the magnitudes of currents to voltages. It doesn't give us the angle relationship. The thing we're really after is the impedance that relates the phasors themselves. And remember, these are complex numbers encoding the magnitude and angle of the voltages and the magnitude and angle of currents throughout the circuit. And that's what we're trying to find. So recall, this is what we've just said on the previous slide. So nothing new here. I just put it up for reference so that we can now talk about how to find impedance. Impedance captures the effect of reactance, but also the phase. So I want an expression kind of like this, but I want one that also captures the phase shift between the voltage phase and the current phase. And I've done that down here at the bottom. So the phase relationship is 90 degrees. Whatever the voltage phase is, you add 90 degrees to get the current phase. Or if you know the current phase, then you subtract 90 to get the voltage phase. How do I subtract 90 degrees? Well, I use the multiplication property. I know that if I multiply by the magic number minus j, then minus j is 1 at an angle of minus 90 degrees. So it's going to take whatever I have here and shift it by negative 90 degrees. And then I take this minus j and I incorporate it into this formula. And for traditional reasons, I don't write it as minus j over 2 pi fc. I write it as 1 over j 2 pi fc. Sorry about that. That's just the way tradition goes. If you want to understand why those two things are equivalent, just multiply top and bottom by j. In the bottom, you'll get j squared, which is negative 1. In the top, you'll have j. You can take the negative 1 and pop that up here. This is why math is so hard and so hard to cover in a slide. If you're doing it on a blackboard, it's a whole lot slower. But you do have the ability to pause the video and think about that if you want. Or you can just now look at this and say, okay, I understand. This is the impedance Z sub C. This is the reactance. It doesn't have the J. This is the impedance. It does have the J. What does the J do? It shifts the phase from current to voltage by negative 90 degrees. And just for completeness, Z sub C could in general have a real part and an imaginary part. So I've rewritten the expression here on the right-hand side as I times the quantity 0 minus jxc. This would be the general form of a complex number, a real part and an imaginary part. I only did that to pull out the fact that in general, z is going to be a full complex number with a real part and an imaginary part. Indeed, in real-world capacitors, this real part here might be non-zero. They have what's called an effective series resistance, an ESR. And you can look that up in data sheets, and sometimes it matters in a circuit. But the resistance in an ideal capacitor is 0. All right, with the complex number and phasor machinery finally in place, let's do something useful. Let's analyze this circuit in detail. From previous episodes, hopefully you recognize this as a voltage divider, except in this case, instead of a resistor here, there is a capacitor. And the useful thing is that capacitor's impedance changes with frequency. So at low frequencies, it may be very big in magnitude compared to the resistor value here. And if it's very big, you don't get much voltage division, the signal goes on out. At high frequencies, when it becomes smaller than the resistance, it's going to, quote, short out the signal. But we don't know exactly how much, but now we can find out exactly how much. And we can also look at phase shifts. So to do that, we use the capacitor impedance, which we now know is 1 over j 2 pi fc. Here, f is in hertz. Sometimes you'll see this formula rewritten as 1 over j omega c, where omega is frequency in radians per second, which is just 2 pi f. I'm going to use the second expression simply because it's less writing. I don't have to write 2 pi f everywhere. I can just write omega. All right, this is a voltage divider. In the upper right here, we have the voltage divider formula that maps the source voltage Vs to the output voltage Vo. Now, these are phasors. Everything in this expression, except for r, is a complex number. Actually, r is a complex number. It just has an imaginary part, which is 0. So everything here is complex math. What I do is I take the expression for the impedance of the capacitor, in this form, in this case, and I plop it in everywhere I see a ZC, and I get this expression. And then everything from this point forward is algebra. But I'll walk you through a little bit of how I got to the final result and why. First of all, we don't usually like compound fractions, so I'm going to multiply top and bottom of this expression by j omega c. That's how I got from here to here. And then I went back to a compound fraction, which seems kind of dumb, but there's a reason for this. This is a standard form that you will often find filter expressions written in. I've defined a new thing now called omega naught, which is the so-called corner frequency. The expression for it is over here on the right. Omega naught is 1 over RC in radians per second. If we were doing this in hertz, which is what the bottom expression is, it would be 1 over 2 pi RC. So to go from this expression with omega in it to this expression with f in hertz in it, I just used these two expressions over here. I'll let you work through the algebra of that if you want. So the net result is shown here. One other thing that's different is that this was an expression for V out, whereas this is an expression for the ratio of V out to Vs. That's what we call the gain or the frequency response or the transfer function of the circuit. It's the multiplier that takes us from the source phasor, the source voltage, to the output voltage. So this expression right here is just the voltage divider portion up here without the Vs. And we call that the gain of the circuit. So if the gain of the circuit is 1, it means that V out is 1 times Vs. I can multiply the Vs on both sides again, and I'll see it's 1 times Vs. But if this expression is, say, 0.1, or some complex number where the magnitude is 0.1, that means that V out is 0.1 times Vs, so the gain is 0.1. So electrical engineers and indeed in many careers, we talk about gain rather than the absolute value of the output. I don't want to know the absolute value. I want to know how the thing transfers whatever Vs is to the output, and the transfer function is this. And this is the term that we have plotted on the cover slide in this episode, and what we will see here in just a minute. So now we're going to take that expression and we're going to come up with the frequency response plots that we showed on the cover slide. And I've shown this as a third part, but this part is much shorter than these, so we're almost at the end. Promise. But this is the important stuff. This is the result. This is the goal we were trying to reach. We now have a circuit which is very common. We've covered the mathematical machinery for coming up with this expression for the so-called gain, the ratio of the output to the input. But what is this? It's a complex expression. Well, there's nothing complex about it. It takes the input signal Vs and changes it in two ways. One, the magnitude, and the other way is the angle. That's the only way in which it is complex. So, what I'm interested in is the magnitude of this versus frequency, and the phase of this versus frequency. And I've plotted those on the right. How did I do that? Well, I plugged in values of f over f naught, so numbers like 0.1 for f over f naught, meaning f is 0.1 times f naught. It's lower than f naught by a factor of 10. And then I tried where f is equal to f naught, and then I tried when it's 10 times f naught. And that's what I'm using to plot on this axis. But I've only labeled f naught here. I'll talk more about the other frequencies in a minute, but I've only labeled f naught. So what do we get at f naught? If f is equal to f naught, this is 1. And I have 1 plus j1. That's the complex number square root of 2 at an angle of 45 degrees. So I have 1 over the square root of 2 at an angle of 45 degrees. So what's that equal to? The magnitude is 1 over the square root of 2. That's 0.7071. So if you go out here to intersect the curve and drop down, or vice versa, here, it shows as 0.7071 for the gain or transfer function at the corner frequency, f naught. Remember I said this will be 1 over the square root of 2 at an angle of negative 45 degrees. Well, that's the phase plot. So at f naught, come down here, go over, and it's negative 45 degrees. At low frequencies, this term will be very close to 1 for reasons we've demonstrated in some of our problem sets. And so the magnitude is going to go to 1. And if you look back at those problem sets and think about things, you'll realize that the angle at 1/10 the corner frequency will go to negative 5.7 degrees. So we just plug in a bunch of different f values here and compute what the value of the gain function is, and then plot the magnitude and the angles. And once we have those plots, we can read off what those magnitudes and angles are at any frequency. And that's what people like to do with frequency response plots. All right, anyway, this is where we were trying to go in this video. In a future video, we may talk about how to actually plug numbers in and use a calculator to get the results. And modern calculators can treat complex numbers as just regular numbers. You can store them as a unit. You don't have to have the separate parts broken out. But they do have different ways of displaying the number and different ways of entering the number. This is a TI-84. This is from the TI page. Here is a Calc-84, which is a cell phone app that I downloaded that emulates kind of what is done in the real-world TI-84 calculator. So I downloaded it, and I found out that, well, you could display complex numbers in polar or rectangular form, like here and here, but in order to enter them, you had to use the exponential notation, which I personally don't like. I wish they'd done it differently. I can kind of understand the reasons they did it, but anyway, in order to enter a number like 2 at an angle of 45 degrees, you actually have to punch in 2 e to the 45i pi divided by 180. And then that comes out to be 2 at an angle of 4.5 times 10 to the 1, which is 45 degrees. So you have to enter it this way, as far as I can tell. If you know differently, then maybe leave a comment below. Another complex number calculator, a good one, is one that I bought when I went back to grad school, and that's shown here. This is the original HP42S. And you can enter complex numbers in either form, and you can display them in either form. And for me, it just works really nice. So to enter this number, what you would do is you would type 4242 and then enter, and then 41, and then second complex, provided you had set the mode to be rectangular format. So needless to say, there's a lot to learn with either of these calculators. In this particular case, this is a so-called RPM calculator, and it works a little different than the TI ones. So you probably won't like it unless you want to learn something completely new. It has a lot of advantages over the so-called algebraic calculators like the TI, but it does take some getting used to. Fortunately, there is a free version of this you can get for this is my cell phone, and there's a free version you can get, and it's called Free 42. So you can read about it at this link, but you could also just go to the Apple Store or the Google Store and download this thing. Also, this was such a good calculator, it's no longer made, that a company called Swiss Micros now has a version of it, hardware, that you can buy, provided you have a fair amount of money. It's in the US, it cost over $200 to get one of these, but it's amazingly cool. If you do choose to punch in some numbers here and try to recreate these plots, I want to warn you, you will not get this plot exactly the way I've drawn it, at least if you use a linear scale for the frequency axis. When I plotted this, for the sake of this video, I was employing what's called a logarithmic scale, and I didn't show it because I didn't want to get into that. We might make another video on different ways of plotting, using semi-log, log-log plots, as well as dB versus log frequency and so forth. I didn't want to get into that, but just be warned that you may not get exactly this graph. It'll do this, it's just that 10F would be way out here on the right, and I didn't want to go that far out. It would be hard to read, so I pushed what happens at 10F to be about here, and that's okay because on a log scale, this could be 10F, this could be, sorry, 10F naught, this could be F naught, this could be 0.1 F naught, this could be 0.01 F naught. Anyway, that's logarithmic scaling. And I don't want to get into that today. We'll maybe do that in the future. So, if you made it this far, thank you for watching. There are some homework problems if you want. If you don't, then thank you for watching and hope to see you in another video. If you want to do the homework problems, here they are. This is from this application. There was a filter here, and we can now analyze it. And so you could do these problems. Figure out what the impedance is in this filter. This is a voltage divider with Z1 here and Z2 here. And so the first step is to figure out what Z2 is. So what's the impedance of this? And maybe we'll discuss this in the comments. Maybe if somebody has questions or has a proposed answer and so forth, maybe we'll discuss it in the comments. Here is a series LC circuit. We haven't talked about L much in this video. L is just like C, except that it's a plus J. And the formula is J 2 pi FL instead of 1 over J 2 pi FC. But I've already worked out what the impedances are at these frequencies. Here's another circuit. This is from Impedance Matching in the Radio Design 101 series, episode 2. The homework problems deal with this output matching network, and they're shown here. So again, do pairwise reductions on this thing. So I would find the impedance of this in series with 50 ohms, negative J380 plus 50, and then put that in parallel with this and see what you get. And then likewise this one, see what you get. Put these two in parallel and then add that to this and then find the net result, the impedance. What is it? So that's your homework assignment if you want. Thanks for watching.